Everyone, you've asked about it, and now we're going to talk about it. Vertical springs. Vertical springs is same with oscillations and going from amplitudes to equilibriums and back. However, there's one extra thing you have to focus on and worry about. You have to worry about the force of gravity. Before, it was just spring forces equaling out at equilibrium and being max at your amplitudes. And our energies were very nice and easy. It was potential energy and kinetic energy, potential in the spring. But now when we oscillate in simple harmonic motion, vertically, we've got to worry about this force of gravity. So the very first thing you might want to figure out is what is the K value of your spring. And solving for that K value is really pretty easy. You want to hang the mass and get to your equilibrium point. So let's show how that's done. If I take a mass and hang it on the spring, and make sure there is friction to stop the motion, you can see right here I've got a 250 gram mass that is stretched at 25 centimeters. So at that location, I'm going to call this my equilibrium point. So everything that happens from this line will be the amplitudes from my equilibrium here. But at this point, I know that the spring force equals the gravitational force. So very simply, I could say that Ky would equal mg. Y being my vertical displacement instead of x for my horizontal displacement. That's the only thing that's going to change there. So right now, I could take my force of gravity and divide by my vertical displacement to get my K constant. And the math works out pretty easily. 250 grams is 0.25 kilos. Let's take gravity as 10. So gravity is 10, gives us 2.5 newtons. 2.5 newtons, it looks like it's divided by 25 centimeters, is going to give us a K value of 10 newtons per meter. So that's the average K value for this mass. What I can do with that now is then take that mass, take off the friction, and put this mass in motion. When I put this mass in motion, I have now stretched it 25 centimeters away from its amplitude, and I can let this move. Now this motion is too fast to watch, so that's the nice thing, is they let us slow down time. We can put it in a quarter time, or I can even put it in 1/16th time. And you can see that when I get to equilibrium, I'm moving very, very quickly. When I move past equilibrium, I start to slow down because the spring is stretched way too much, and then I'm going to come right back up. And if you trace that out as this oscillation is going along, so we're going to go from amplitude through equilibrium, down to our other amplitude, back up through equilibrium, and stop at our other amplitude. So you can see this does trace out our cosine curve that we're used to for masses and springs. The only difference here, instead of an x equals a cosine omega, I would write this as y equals a cosine of theta. And from there you can get your velocities, your accelerations, and the nice thing about vertical springs or horizontal springs, they're going to oscillate the same. So they're both going to be in simple harmonic motion. The displacement will be opposite the acceleration, and we can map that out. But the one thing that may be very helpful for you is analyzing this in terms of energies. So if you look at the energy graphs here, the energy graphs have a lot of stuff going on when this moves back and forth and back and forth. You can see that the kinetic energy peaks right around that equilibrium point and then goes back down. All gravitational energy at the highest point. When it gets all the way down to the negative amplitude, we've got maximum gravitation or elastic energy, which means that they must be making potential energy 0 at the ground level. So the energies are going to flip-flop between all three of these locations. Let's try and solve a problem with this. Let's actually figure out how fast this mass is going when it goes through its equilibrium. So when we analyze our energies here, you've got gravitational and spring energy when you're at equilibrium and at rest. If we make the height equaling 0 at the ground, then we'll have all spring energy at the bottom. And when we reach the highest point possible, we'll be at all gravitational energy. And the reason I know there's no kinetic energy at any of those points is the spring will be stopped all the way down at the bottom. And when you reach your highest point, all your energy is going to be in height and so you'll have no speed there as well. The place where you're going to have maximum speed is when you reach that equilibrium point. So let's try to set this problem up. So here we go. We've got the equilibrium point down here, the mass at 3 different locations as we go along, and we want to figure out energies at each location. So we already know the K value is 10 newtons per meter from the simulator, and I took this all the way up to an amplitude of 25 centimeters. So my amplitude above will be 25 centimeters, and my amplitude below will also be 25 centimeters. So when I think about what kind of energies I have at these different locations, there's 3 energies to keep track of. You've got your gravitational energy, you've got your elastic spring energy, and you've got your kinetic. When we look at that highest point, we know that the mass is stopped, so we're not moving. Kinetic energy equals 0. We also know that if I'm at the highest point and the spring isn't stretched, there's no energy in the spring. So that means all my energy here must be just m, g, and h. So if you take your mass of 0.25 kilograms, we know gravity, and I've got 25 centimeters as my height above equilibrium, which means I'm a total of 50 centimeters above the ground. My total gravitational energy turns into 1.25 joules. Now, since we're not going to have any friction or damping in this problem, that 1.25 joules is going to stay with the object as it moves back and forth. So why don't we go to the extreme? Let's go to the far extreme when it gets down to negative amplitude. At negative amplitude, our gravitational energy is going to drop to 0. Our kinetic energy at the lowest point is also going to be 0 because we're not going to be moving, and our elastic energy is going to be equal to whatever energy the system contains, which is 1.25 joules. My spring energy is all that gravitational energy that I had in the beginning. So if I would try to solve for things, I could solve for how far the spring has been stretched. The spring down here must be stretched from my 0 point 50 centimeters. So if you put 50 centimeters in for your stretch, you put 10 newtons per meter as the K constant, you will get 1.25 joules of elastic energy. So those are the extremes, and those are the easy parts. The difficult part gets to be the middle. And when we're in the middle, we've got lots of energies going on like you saw in the simulator. We have elastic energy because I'm stretched from my 0 point. We have gravitational energy because I'm a height above the ground. And we're going to have kinetic energy because that mass is going to be moving. We have all 3 energies to focus on at that location. Let's figure out how much energy is in each spot. Well, gravitationally, it's just mgh. And your mass is 0.25 kilograms, gravity's 9.8 or 10, so it's about 2.5 newtons multiplied by 0.25 meters. And when you do that math, you'll get around 0.625 joules of our 1.25 total. The spring, when you look at the spring and you figure out how far it's been stretched from its unstretched length, that's 1/2 kx squared, you get about 0.3125 joules, which means if you add those two up, it's around 0.93 joules of energy that are in gravity and in the spring. But the total energy was 1.25 joules, which leaves about 0.3125 joules of energy in kinetic energy. And now that we know kinetic energy, you can use 1/2 mv squared to figure out how fast the particle is moving. To figure out how fast it's moving, you'll do your work and you should get a maximum velocity of 1.58 meters per second. So I like using energy because I can visualize where the energy is at different locations based on spring compression or stretch or heights, and from that I can use that information to pull out how fast the particle is moving. So as this mass oscillates up and down from its equilibrium point, it'll have no velocity at its peaks and it'll be moving as fast as it possibly can at the equilibrium point. And the reason for that is that spring force is growing. The forces are not balanced until you reach equilibrium. So even though the spring is stretching, you still continue to pick up speed, kind of like an air drag on you, until you reach that equilibrium point. Once you go beyond equilibrium, the forces unbalance upwards and decrease your velocity until you run out of speed. And then, since you're in simple harmonic motion, you'll just oscillate back and forth with an omega, since you're a mass and you're on a spring, equal to the square root of k over m. And from that, we know how to find your time periods and your frequencies and all the good things that come with simple harmonic motion.